Hi, Kansha.
Hey Marie, how are you doing?
Good. How are you?
I'm doing good. I'm just waiting for a few more folks to join in so that we can start then.
Yeah, no, for sure. We'll give folks a few minutes to join up. And in the meantime, what I will do is I will share a couple of links here. Let me just go to what I want to share as the cloud native landscape
Mhm.
as one tweet. So I'll drop it in your little space tweet here, and then I'll just drop that in the Jumbotron. Okay, got that ready to go.
Hi everyone, I'm Akansha, and today we will be taking a look at the entire cloud native networking landscape. So I'm excited to host this space along with Marino. So, Marino, would you like to give yourself a quick intro?
Absolutely. Thank you, Akansha, for hosting this space. My name is Marino Wijay. I am a platform advocate at Solo. I am a community advocate. I focus in on open source and cloud native networking and even cloud networking. And that's primarily because I've had an extensive background in the networking space, spent a lot of time there, worked in campus environments, wireless networks, data center environments, then cloud and now cloud native. And so, I'm here to relay as much information as I can over the next hour about what the networking landscape looks like today, and some of the technologies that I tend to focus on, along with what Akansha might focus on as well. So I'll pass it back to you, Akansha.
Yeah, thanks for the quick intro, Marino. Let me just begin with a brief background. So, like networking, as you all know, that it is a backbone of any modern technology, and it allows communication between devices and application, whether you are sitting next to each other or on the opposite sides of the world. So, it's just all about connecting things together. So, if we talk about in the context of Kubernetes, it is like even more important because as we know that Kubernetes is a container orchestration platform. This means it's responsible for managing and scaling a large number of containers running in a cluster, and these containers need to be able to communicate with each other as well as with the other parts of the infrastructure such as external services and databases. And Kubernetes networking allows this communication to happen seamlessly and securely. So, for the folks who aren't familiar with the CNCF landscape, it is essentially a collection of various tools and services which you can use in your cloud native systems. And if you head over to the landscape right now, you might be overwhelmed by the number of tools that are listed, especially if it is your first time seeing it. So there are tons of different categories in the landscape. These categories are used to list tools that are used for a certain action. So for example, if you check the service mesh category, you will see ton of tools that can be used as service meshes for your Kubernetes clusters. And it includes options like Istio, Linkerd, Console, and many more. So yeah, over to you, Marino.
Yeah, absolutely. And before I continue your thought there, and by the way, thank you so much for that brilliant introduction. What I'd like to just bring up is that I know some of you might be interested in doing your CKA, the Certified Kubernetes Administrator exam. It's a very tough exam, I will admit. I've taken that exam years ago, but back then it was about 3 hours, and we've come a long way with a lot of enhancements in Kubernetes. Now, our good friend Siam had written a handbook on the CK very recently, and he's published it and he's made it for sale. I've gone ahead and picked up 10 copies that I am happy to give away. If you could actually reply to this Twitter space and tell us why you're looking to get into the cloud native ecosystem. I know this is going to be a networking focused session, but I want to encourage you all to find your path in cloud native. And I think going after the CKA is an excellent challenge for yourselves. I went through it, it's hands on, it's very fun. But at the same time, tell us your story. Tell us what you're looking for. If you're studying for the CKA, this book will help you. I've already had a preview of it. It's an excellent book, takes you through some key concepts as well as being able to get through the exam. So, tell us your story. And at the end of the day, I'll run a quick random picker, and then we'll pick 10 people who gave some really good stories about their journey to CK and cloud native. All right, let's get into networking. So Akanshik laid out some very good foundational knowledge around why we need networking and what Kubernetes is doing. Let's back up a bit, right, to understand the why behind networking. So within a device, whatever a device it is, you might think of your iPhone or Android device or your laptop, even very small handheld iPads, whatever it is, right? Every single one of those devices has its own little internal network, and we may not have direct access, and we actually normally don't have direct access to that internal network, and that's because it's a very highly customized and tuned network because that network acts as a bus where multiple components communicate with each other to effectively give us some sort of output, right? So behind the scenes on my iPhone, because I'm communicating through it for this Twitter space, in my iPhone, there might be some inter-process communications going on, and it's happening in its own little network before all of this data that I'm sending to you right now through this voice gets to you on your end on your Twitter app or your wherever you're listening into this space. So when you get beyond that, right, we're talking about different devices needing to be able to communicate to each other. And over the many, many years, we're talking about 4 decades worth of innovation. What we've seen is how networks have evolved and gone from private to private and public, so that there's security built in, there's the ability to scale, there's the ability to just create on-demand artifacts when we need to and have them allow them access to the network. But how does this all start? Your device right now is connected to some form of network. It might be a wireless network. It might be um, let's say a 5G or LTE connection, whatever it is. Um, what ends up happening is you're terminating at some sort of core device that knows how to get you and your device to other networks, to other locations, to other destinations, because your device doesn't know about the rest of the network. It doesn't know about this global scale. So there are devices in between your device, your iPhone, your laptop, your MacBook, whatever it is, and my system or a server or a cloud service that you might be accessing. And those devices, those intermediary devices, are actually moving your requests throughout the network to make sure they get to their destination in the fastest manner possible while still providing you the result in a timely manner. So we've improved upon this over many, many iterations and years, especially when it comes to these intermediary devices, because these intermediary devices that I'm talking about are physical devices that exist at data centers, in cloud environments, at points of presence or POPs or service provider locations for that matter, and they control a big aspect of the internet. Now, when we think about networks and the connectivity streams itself, I mean, it's very, very challenging to try and navigate a network or build on top of existing networks because of so many different constraints we have to consider. And so technologies have been built on top, software technologies to accommodate for what the physical world is doing, or the way the physical world moves our packets around. Now, going back to those intermediary devices, I call them routers and switches because they're effectively ones responsible for moving packets around very quickly and knowing how to decide where to move those packets to. That's effectively the function of a router and the usage of or the paired usage of a switch. Now you're going to see this at scale. But the reality is us as consumers of the network don't have direct access to these devices. We do have devices or access to devices that we get to control, and that we get to configure and that we get to connect to these public facing networks. But outside of that, we have very limited control. So what we're doing now at this point is leveraging software paradigms to effectively bridge disparate networks. And that's what tools like Service Mesh or VPN tunneling or container networking interfaces are actually providing for you. It's just we don't really see a lot of those details because at the end of the day, you're presented with a network, you connect your device, and you're on your way. And that's where cloud native has gone, that's where cloud has gone, that's where the physical world has gone through iterations of faster chips, faster circuits. So we're talking about 10 gig, 100 gig, 400 gig in the data center. That's moving a lot of our data. Now, anyways, let's get a little bit more specific, right? I talk about a lot of this stuff at a grander level because when we get into the cloud native landscape, there are several different areas that we want to focus in on, right? Those several different areas still depend on the physical network. So let's be a little bit more specific. I want to run a Kubernetes cluster today. I might decide, let's run this Kubernetes cluster in a cloud provider, let's say Google Cloud, AWS, or maybe even Civo Cloud for that matter. Now, any one of these cloud providers give you direct access to the public world, public internet, meaning anytime you spin up a cluster, there is the potential for it to have access to the outside world. And that's great. But what actually has been provisioned when you deploy a cluster? Well, when you deploy a Kubernetes cluster somewhere, you need a physical network because in that cluster, there are nodes that need to communicate amongst each other. Now, like I said, we don't normally have access to physical networks all the time, especially if they reside in the cloud. So, what the cloud gives us is this concept of being able to build virtual networks. If you're working in AWS, you might be familiar with the concept of a VPC. Google Cloud calls them cloud VPCs. Azure calls them VNets, and I don't believe Civo has an official name for them, but effectively it's a network and it's a virtual network inside of Civo Cloud. Now, these virtual networks can be built repeatedly and automated because it's just software. And that grants us the facility to go and land Kubernetes nodes into this virtual network. Because these Kubernetes nodes are effectively just virtual machines that need access to the network, they'll be tied to a virtual network. We can go branch off into this whole virtual networking concept, but um, if I do, that is a tangent on its own. And let me spend 5 minutes talking about virtual networking for a second. The reason why we got to virtual networking is because we realized we had so much capacity on our devices, but we were only using maybe 5 to 10%. It's very much like the virtualization paradigm with compute and physical hosts. We take hosts, we load up a hypervisor, and now we can load up a bunch of virtual machines. Now, in the world of networking, there's a very similar paradigm. When we want to create multiple networks inside of, let's say, a switch, what we would probably do is create VLANs or virtual LANs. Now, these virtual LANs, there are many out there. We could go up to, I think, 4,096 virtual LANs in a single switch. And that's something that's specific to a switch. And what that represents is a subnet, an IP subnet. That IP subnet gives us the ability to grant addresses directly to our hosts that allow them access to the network. So if I can have all of these different VLANs, I can configure, connect them, and whatnot. This is great. I've virtualized some of my networking. But the virtualization actually didn't stop there. The virtualization went beyond VLANs and went to this concept of software-defined networking, where we were creating virtual network functions like virtual routers, virtual switches for that matter, and even virtual routing topologies. So what's interesting about this paradigm is that all of that lives in software. So the concept of software-defined networking is effectively what I just described. If you wanted to build a network in software just in time, this concept of software-defined networking allowed that because there were protocols that were built to enable this. One particular protocol that some of you might have heard of is the VXLAN protocol. It effectively allowed you to create a virtual network on top of a virtual network. Why it does that is because this allows us to span geographically or maybe through different IP subnets and carry our logical networks wherever we want them to. This allows us to then say, hey, if I want to define my network as YAML and then provision that to, let's say, an environment, I absolutely can do so. And I can do so in a very repeatable fashion. Using virtual networking or this concept of software-defined networking also enabled some interesting strategies around disaster recovery. So when it comes to disaster recovery, there was a pain point around retaining IP addresses and making sure that when you had to recover, You didn't have to change the underlying networking stacks. Now, that's a problem that some organizations might continue to face, but we've gotten way past that because of DNS. DNS allows us some very powerful capabilities around having to translate names that we read, like a website, to an actual IP address. And if we can map multiple IP addresses behind a DNS name, we can also do some load balancing there. Anyways, so with virtual networking and software-defined networking working together to provide us, this network that lives in software, we were able to really build out some strong, scalable, secure cloud environments because we would write everything as code. And this is very, very coupled with this whole notion of infrastructure as code. Now, fast forward to 5 years ago, no, 6 years ago, when we started seeing a lot of noise around Kubernetes and containers. What ended up happening was we had these container artifacts that, they're isolated processes that could run on your local system. They could run on an orchestrated system. It doesn't matter. But these processes still need access to the network. So how do you give these processes access to the network? You can't just simply wrap it in a VM because a VM is too bloaty. We're again in a VM only maybe using 10% of that resources allocation just for a single process. So we containerize it, but how do we still give access to a network? In the Linux operating system, there's this concept of networking namespaces, basically allowing us to create virtual network endpoints that allow us to map to a process. So you wrap a process inside of a networking namespace, and it basically is its own little entity that has a network endpoint and that has a process attached to it, it's still pretty stateless at this point. But because we have network access to it inside of my Linux operating system, I could create a bunch of those network namespaces and have all of these processes communicate amongst each other. And then I could, turn on NAT on that Linux operating system, and do some internal routing. And now these network namespaces have access to the outside world. These networking namespaces are actually pods in Kubernetes. The process of creating a networking namespace is actually very tedious. It's toil. It's endless toil. And as we know with containers, we expect them to be ephemeral. So they'll come and then they'll just go at any time. And that's this whole notion of what DevOps is doing, right? Or cloud native. We expect things to fail and something else to reconcile that for us. That's what Kubernetes is doing for us. But when it comes to networking, what we have to consider here is that we don't want to be repeatedly creating networking namespaces for every single container and then having to destroy everyone. We could automate it, but then we have this disparity in the way we go about in automating it. So, Docker definitely did this really well. They built out a way to build networking namespaces, made it proprietary, obviously, but allowed you some significant flexibility in how you build networks for your Docker containers. When we translate this to Kubernetes, we wanted to make sure that there was a specification, a guideline that everyone would follow and conform to, but you could go implement your own container networking interface spec the way you wanted to. What that meant is you had companies like VMware, for example, or you had companies like AWS, or you have companies like Tigera, or even Isovalent that put together open source projects, open source container networking interfaces that effectively just do what I described around networking namespaces. So it automates the process, provides some IP address management, so you don't have to worry about a DHCP server in the mix. And now you have an environment that runs Kubernetes, has a container network, and your pods can communicate. It doesn't stop there, though, because even though your pods have access to a network where they can communicate amongst each other, that's not the paradigm we go for when it comes to designing a network for Kubernetes or for our microservices, because then we also have to consider the way we give access to outside resources into our cluster, better known as ingress. We also have to consider how we filter some of those requests coming in and out to our cluster. This is where something like a service mesh might come into play here. But we also have to consider the underlying infrastructure that we still need for some of this activity. Now, in Kubernetes, there's this concept of services. There are three types. There's cluster IP. There's actually a few. There's cluster IP. There's node port, and then there's the load balancer service. We'll visit the third one in a second in more detail, but the first two, the cluster IP functionality, just internally exposes pods, meaning only internal resources can access pods through a service name. Now, a service in Kubernetes is an actual way to translate DNS. It's not directly called DNS, but it's a way to translate DNS into pod IPs. They use this concept of labels and selectors to effectively map a service to specific pods that you might have deployed. Now, in a manifest, you'll have a deployment, and that deployment itself would have the label selector that the selector would be picked for the service object that you create for it to expose that service. Now, node port just ties it to a specific node, and why that can be limiting is because your nodes can come and go pretty easily, and you don't want to be in a situation of, you lose a node, and what the heck do you do at that point? Now you've lost access to your app. And this is where the load balancer service comes in, because the load balancer service is something that a cloud provider would give you a load balancer, whether it's a network level load balancer or an application level load balancer, that your Kubernetes cluster can access and basically tell it to say, look, if I'm exposing services here and I'm trying to allow certain inbound requests to come to my pods, well, I want you to listen for that. That's effectively what a load balancer is doing, plus some other stuff around high availability as well. Now, once you have these pieces in the mix here, you've got pretty much what you need to get going for a Kubernetes cluster, and you've got the right pieces for the network, right? You've got inbound access. Your pods can get outbound if they need to. There's still the element of security that we haven't talked about, and then there's a couple of other things that we have to really dive into. So ingress and service mesh are probably those that are going to be discussed next. But I'm going to stop there, and I'm going to pass it back to Akansha just to see if you have any thoughts here, or if you like to ask any questions.
Thank you, Marino. Like you covered a lot of topics, starting from the main introduction and setting up the basics of networking along with virtual networks and going into so much details about Kubernetes networking and so on. So the next thing, if we could move on to service mesh functionalities, that would be great.
Yeah, absolutely. So right before I get into a service mesh, I also want to talk about the ways we communicate with our applications. Normally,
Okay.
we would communicate with those applications through HTTP, right? We're not going to directly call on something on its IP address and say, hey, I'm going to ping this address. That's not how services communicate. What ends up happening is there's a service call from service, let's say A, over to service B, and that might be an HTTP request method, let's say a GET method, to get some data from service B. And service A is going to take that data and then pass it along to someone on the outside. Service B is just responsible for generating the data or the output. Now, that communication can be HTTP, it can be other protocols, but for the purposes of, and the majority of what we do is going to be around HTTP based communication. Now, HTTP lives at layer 7 of the OSI model, which I didn't discuss earlier on, but the OSI model is a model that represents every layer of a network, the physical layer to the network layer, all the way up to the application layer. The physical layer is something I touched on very early on when we're talking about physical devices and electrical signals. The network layer is where we're addressing every single endpoint and effectively using logic to route these endpoints, or the requests they make to the necessary destinations. But there's not a lot of intelligence that we have at the network layer. So we have to look at the intelligence at the application layer, because when we leverage HTTP, we can make some very interesting requests and pass along some interesting data. Data can be like, I can pass along authentication so that I can auth myself into the service versus just going in, anonymously. And so that is a security pillar. Like, that's part of the security stack when it comes to how we operate inside of a microservices environment with various services. But if I think about authorization from it, who's basically taking care of that? Who's going to be responsible for that? There's also the element of filtration, right? I have all of these services that communicate with each other. Need a way to filter who doesn't need to talk to, some other entities. You have one service; it doesn't need to talk to anyone, but maybe another service. So we want to lock that down. There used to be this. I mean, it's still pretty much used. It's called microsegmentation, and it was a term that basically locked down every single endpoint to the necessary ports that it needed to communicate on. When we're talking about TCP or UDP ports. But that being said, right, like there's not a lot of telling information in TCP and UDP, so this is where we look to layer 7. Layer 7 can give us some very powerful information around how we want to process the request. Do we want to reject the request because this particular requester didn't present a certificate in its request? We can't do that at the network layer. What we can do at the network layer is filtration at an IP level or a host name level. But that's not enough. That's not true defense in depth. That's part of the way we block access to entities we don't want in our network. But the layer 7 piece gives us this ability to inject identity, right? We can inject some identity and pair that with authorization. So now we have authorization along with authentication. And this is a very powerful feature of what a service mesh does. A service mesh, though, is much more than what I just described. It actually is meant to help with access to APIs or services that exist in your environment or your cluster. So a service mesh specifically, the way that it operates is it deploys a few entities here. It deploys a control plane called it can be anything. I mean, any service mesh will do this, but it'll deploy a control plane that effectively communicates with the Kubernetes control plane to understand what it knows about. And the same control plane will effectively influence certain things about the way the architecture or infrastructure is going to look. The control plane is also responsible for passing along configurations and direction to the data plane. Now, the data plane inside of a Kubernetes environment, we know it as a CNI. It can also be proxies that exist inside of your Kubernetes cluster. These proxies can be an ingress proxy or an ingress controller of some sorts, or it can be an ingress gateway that a service mesh might provide. There can also be an egress gateway as well, so that you can control what traffic exits your cluster. And then within a cluster, all of your services get their own little mini proxies. I mean, this is an optional configuration too, given the recent developments in the cloud native space. But you can deploy these mini proxies that allow you to stick kind of like a router that sits alongside of your main container. This router is going to be the one that's responsible for routing all your requests and filtering requests and even policing and authorizing requests into and out of that service, which is actually pretty damn powerful when you think about it. This is what a service mesh is effectively doing. It's effectively allowing you to decide how to route to different resources, not based off of just IP or hostname information, but also based off of that HTTP header information. So there's some intelligence that a service mesh will pick up from Kubernetes. Like it'll know about all the pods, it'll know about services that exist inside of Kubernetes. So the services that you've decided to expose. But you would control the way you expose your services through something called an ingress gateway that a service mesh would provide. And you would just map your services to resources inside of this ingress gateway and then basically provide a path inbound. Now you have at this point multiple layers of networking. What's going on here? You have a physical layer, a physical network that is just simply moving around electrical signals based off of logic provided to it. You have virtual networks that have been constructed to manage your nodes and even allow access to the outside world. These are those software-defined networks I described. And now you have a Kubernetes layered network, which on one hand, you have this CNI network that effectively allows your pods to communicate to other pods. And then you have a service mesh layer that allows you to control intelligently how you access your services. filter them, provide authorization, provide even encryption between services using this concept of mutual TLS. Um, but that's not, the only things a service mesh offers. A service mesh goes well beyond that to help with things like blue-green deployments or dark launches or canary launches. It helps to build resilient services so that, let's say inside of let's say you're trying to access an application. That application might be comprised of 10 different microservices, and they need to communicate amongst each other, or there might be a path that each one of these services has to take to reach to another service to ultimately give you a result. Now, in certain situations, part of that application could break because, I don't know, a pod failed, ran out of memory, or the underlying node failed for whatever reason. What a service mesh can allow you to do is circuit break and work around the failed object and still provide you a partial result or a partial output. You might be missing some pieces of it, but that one piece might not be so critical. And it might be telling of maybe you need to provide some more resources in your cluster so that your pod can continue to run. Maybe you need to scale the pod to have multiple copies of it, and then you'd load balance across those two. But what's very, very interesting about this all is that Kubernetes is going to be ultimately responsible for reconciliation all throughout. What is reconciliation? So Kubernetes expects things to work in a certain way based on what you tell it, right? This is the declarative model. I want certain things to look a certain way. Kubernetes, please honor it. Now, if there is any sort of, uh, you know, divergence from that, or if there is something that's amiss or something that seems off, Kubernetes will work to reconcile that. I mean, obviously, what Kubernetes can't do is reconcile a node that is offline. That's going to be the responsibility of the underlying cloud provider, which actually Kubernetes has hooks into through APIs and whatnot. It'll communicate with the cloud provider's API and then tell it, hey, a node failed. Can you please reprovision another node and add it back into our cluster so that I can continue to spin up new workloads? And what's magical about this is that the underlying networking is actually taken care of for you. So there's a lot of automation that happens here behind the scenes that we normally aren't privy to, but you can actually go and dissect this if you decide to and go into, let's say, AWS and determine how your VPCs have been constructed, if you've deployed any sort of NAT gateways or NLBs or ALBs to support your cluster. If you run EKSETL create cluster, it's actually going to talk to the AWS API to provision EC2 instances along, or an EKS cluster along with your load balancer, and that EKS cluster is actually provisioning EC2 instances behind the scenes, which you don't see. And you could still go witness it if you wanted to, because there are associations to that cluster through the name. But a lot of this is automated, right? And if you think about the networking that I described earlier on around networking namespaces, that automation is prevalent throughout the entire stack, from the physical world all the way up to that service mesh layer. Why that is, though, is because you would probably want to consider using GitOps as a mechanism to automate parts of your network as well and reconcile parts of your network that don't seem right. So we've got these four layers: the physical network, a virtual network or a software-defined layer network, the Kubernetes underlay, or the Kubernetes network, which is the CNI network, and then your service mesh layer. So those are four areas to dig into. We can go on forever, but I'm going to pass it back to you, Akansha.
Thank you, Marino. So, like, there's one question in the audience from Siddhant, so I will take that up. So, how would you approach a troubleshooting a network problem? From what I understand, if the API server isn't able to talk to any other components, it would be impossible to do anything in the cluster. So, how would we troubleshoot the problem if it's a network issue or misconfiguration? So, Marino, would you like to answer that?
Yeah, absolutely. So there's so many ways to try and troubleshoot this particular issue. My method would be to first see if I have access to, let's say, the control plane node. And if I do, if I have access to root into it, or SSH and root into the node itself, then from that perspective, I should be able to determine if I have outbound access. The other consideration is, like, where is this control plane sitting? Why is it separate from the worker nodes? And if it is separate, right, and if we're talking about remote networks where you have your control plane on one network and your worker nodes on another network, there might be some sort of device in between that might be filtering the way your control plane communicates with your nodes. What that device might be is a firewall. That firewall might be blocking all ports. Now, I'll be very, very honest with y'all. I don't remember all the ports that Kubernetes needs to communicate across. But if you go to the Kubernetes docs, it'll actually tell you the specific ports you need to know to ensure that your control plane can communicate with your nodes. Anyways, there's a firewall, and it's not allowing the particular ports the Kubernetes control plane needs to talk to the worker nodes. That's one reason why you might have a lack of communication there, right? There could be an underlying network problem with the node itself. Maybe it's not connected properly to the rest of the network. Maybe it's missing a default gateway and it can't route out to the rest of the world. Or maybe someone, for whatever reason, put in a static route into that node and said, hey, if you're trying to go to a default route to go anywhere, take this route. That could be, someone who just has hijacked or compromised your node and effectively has thrown a some sort of logic into your box to say, send all traffic elsewhere so that I can capture it and I can be very malicious with this traffic and do something with it, which is normally known as a person in the middle attack. So, there are a variety of ways to consider troubleshooting. Heck, if you know these devices are on the same network, there are tools like Wireshark or TCP dump that you can use to decipher whether or not your traffic is reaching its destination and if the protocols are getting through. There could be a lot of different things going on as well. If you look at your nodes, right? If you have access to your nodes, can they communicate to each other? Can they communicate outside, right? If there's a node miscommunication, maybe it's not network related. Maybe there's something wrong with the certificate that has been issued from the control plane to the nodes. Maybe it wasn't distributed correctly. There's so many different ways to look at this, but I would always start with the control plane if I have access to it. I mean, working from my own system, I could see if I have access to these nodes, can I reach any of these nodes or control plane nodes for that matter? There are various ways to go ahead and troubleshoot.
Thank you, Marina. Hope this answers your question, Siddhant. So we have the next question, and by Chandra, and he says that sidecar proxy is one of the design patterns I used in service mesh technology using Console, one of the CNCF tool. Could you also say a few things on it?
Yeah, so I just described what service mesh is, and I mentioned this concept of mini proxies. These mini proxies are effectively the sidecar that you're specifically referring to. So these sidecars are just another container inside of your pod alongside your main application container, but the sidecars are proxying all connections and communications towards the main container. So when you actually send traffic to let's say one of your pods, the first entity to intercept it is that sidecar container. And that sidecar container will process it and then forward the traffic on to the main application container. And what's interesting is those two containers share the same networking namespace. So they're going to have the same pod IP. Now, if you actually look at the detailed configuration of each container, they're going to be differentiated using port numbers or container port numbers. And that's the way you would communicate with each individual container to differentiate them from within a pod. So that's the sidecar pattern. There's actually sidecarless patterns that exist today through something called, there's a service mesh called Istio, and it offers something called Istio Ambient Mesh, which is a sidecarless pattern, and it still offers the same capabilities as a regular service mesh. It just specifically addresses conditions where stateful workloads don't take advantage of the mesh, or you have, let's say, like a SQL database that really can't communicate at HTTP, but communicates at TCP. Is a situation where you would want to use ambient mesh, or a situation where you would want to avoid race conditions altogether, because sometimes you might have your main application container come online before the networking is rewritten for the sidecar to take ownership of that networking. Now, interestingly enough, that has actually been addressed in Kubernetes 1.27 with the latest sidecar Kubernetes enhancement. That sidecar resource now allows you to indicate to Kubernetes that a specific sidecar should come online before the main application container does, always. So this is something now native to Kubernetes, which is very, very powerful. I hope that answers your question.
Yeah, thanks. Thanks, Marino. So I will shift the conversation to a different side. And it is like there's a classic system admin explanation given when there's something odd happening with a network that it's always DNS. So my question is that why DNS is so hated?
I don't think DNS is super hated. I think it's everyone relies on it and and doesn't realize that they are reliant on it. Realistically speaking, we can't rely on just numbering. We can't number everyone. If I had to remember every single phone number out there in the world, impractical. Even my phone book, I wouldn't be able to identify who's who. Which is why we use names, right? We have names assigned to those phone numbers. So if I'm looking for someone, I don't have to remember their number. I just have to remember their name. This is the same idea around DNS. I don't have to remember the IP address behind it. I just have to remember the name. And why DNS is so dependent is because DNS is actually multifunctional. It's not just a translation of a host name to an address. It's actually a service that is required in various environments because the way we want to be able to communicate with objects and endpoints is by names, not by addresses directly. And so we don't always retain these address books. We don't update them all the time, especially when it comes to systems and even Kubernetes. We rely on something else, someone else to maintain that database for us. So in Kubernetes, there's something called Core DNS, which actually maintains all entries of pods to IP addresses and even services to IP addresses as well. And why this is important is because every time something changes inside of Kubernetes, like a pod goes or disappears, that core DNS is updated. So that entry is removed and maybe a new entry is added because a new pod came online with a new IP and a new host name. So that's something that is reliant. We rely on DNS to consistently give us this information. There are other situations where we may be trying to put together a solution. I'll give you a really good example. Way back when I was working at VMware, I had gravitated towards wanting to build a home lab. So in a home lab, you'll probably get 3 machines that are almost server grade, not necessarily. They could just be 3 powerful desktops or Intel NUCs or something similar. And what you would do is you would deploy ESX on top of each one of those hosts, and then you would deploy a management system called vCenter. Now, vCenter, interestingly enough, expects you to have DNS running. If it doesn't have DNS, it doesn't know how to resolve addresses to your actual physical nodes, your ESX hosts. So you have to point it to a DNS server, which it'll ask the DNS server, hey, can you resolve these host names for me as IP addresses? I mean, vCenter doesn't necessarily need that, but I'm just giving you an example. Now, if vCenter didn't know how to resolve this for these 3 nodes that I have, and it didn't have access to DNS, I have to manually create these static entries on vCenter and say, hey, host 1 is 192.168.10.1, host 2 is 10.2, host 3 is 10.3. And I have to keep maintaining that all together. And that's not something I want to do. Also, if I make a mistake somewhere because of a misprint or a mistype somewhere, that means I might not have access to a particular resource that I might be trying to access through DNS. I might have incorrectly inputted an IP address somewhere, and now that host name is not resolving to the right IP, so I can't get to it. So DNS is critical, especially on the internet, because we are so reliant on DNS. If there is a slight misconfiguration somewhere, there is a possibility that our request might be misrouted somewhere. Now, let's look at DNS from the example of my computer, right? I'm trying to go to cncf.io. What actually happens in that process? So my local host doesn't know the IP address of cncf.io. So it actually has to communicate with a DNS server to resolve that address. The DNS process can be very, very deep, or it could be very simple. And that's all dependent on caching and who's cached these entries. But let's just assume that the DNS server somewhere has resolved the IP address. Now I know the IP address of cncf.io. How do I route to it? So I'm going to use my local host's TCP/IP stack to communicate with my local gateway, which is my default gateway, because I don't know where CNCF's IP address is. I don't publicly know it. I don't know how to route to it, but my gateway does. So now I'll route to that through my gateway. My gateway will take me to the destination, and then it'll do the same for the return. And now the cncf.io website basically renders on my web page or my web browser as a web page. So DNS is required because we will need to be able to know how to route to these resources. And without knowing how to route to these resources and without access to a DNS server, we won't be able to get to those destinations. Now, if we, like I said, if we knew all these IP addresses pretty well, then we could probably easily route to them without DNS. But that's not the reality here. And this is why DNS is very critical to infrastructures, both internal, private, public, wherever.
Okay, so that was very insightful. I can see how DNS is so useful and essential for everything in our networking workloads. So how would you go ahead troubleshooting it? Like what's the first thing you try for doing the DNS troubleshooting?
You can use a set of tools, right? So there used to be this tool in Linux called NSLookup, which is now deprecated and deprecated in favor of Dig. Dig is another mechanism to allow you to resolve host names to IP addresses. So what Dig can do for you is give you this opportunity to know if you can resolve a certain address. If you can't resolve it, why can't you resolve it? Why can't Dig resolve it? Dig primarily uses the DNS server that you have specified for your host. If that DNS server is inaccessible because you don't have access to it or you can't locally get to it, then what ends up happening is you can't resolve any host names. If that DNS server doesn't have access to the outside world, right, then it can't resolve things for you. So if it can't get out to the internet to maybe talk to an upstream DNS server, it might not be able to answer questions for you. So what you can do is if your host has access to the outside world, right, and if for some reason something's not resolving, well, you have the option to specify a public DNS server. For example, dig at 8.8.8.8, which is a Google DNS server, a public DNS server, which knows about all public addresses and host names. And then you can add your host name as a parameter, the host name that you're trying to get to see if it resolves. If it resolves, that means your external DNS is working, which means your host can get out to the internet. Something's wrong with your DNS server, right? On the flip side, it could just be that maybe on your local TCP/IP stack, you weren't issued a DNS server to resolve addresses for you. There are many, many more ways to try and troubleshoot what's going on with DNS. There could be something underlying in the DNS server itself. Maybe it hasn't updated. Maybe it has very stale entries because of caching. Maybe the way how long we've cached things for and we haven't aged things out means we haven't made room for other newer entries into that DNS table. So there's a lot of different factors to consider here. Hopefully that answers the question.
Yeah, definitely it does. Hi Ashwin, like please feel free to ask any questions if you have or any thoughts you would like to share here. Ashwin, are you like you are muted?
Hi, I just joined, so I was just gonna lurk around before I jump in and add my thoughts. Thank you so much for considering.
Uh, no problem. Thank you, Ashwin. So, okay, so Marino, you had mentioned before in the conversations about API gateways. So, would you like to share some light upon that? Like, is it something like API gateway sits on the top of an external load balancer and handle the traffic or is it different? And like, what are your views about API gateways versus service meshes?
Yeah, so an API gateway will definitely sit on top of a load balancer. Load balancer is just something that's going to listen in externally for requests, but the real logic happens in the API gateway as to what happens with that request. Now, an API gateway is a pattern from something years ago, which you'll see API gateway still around, but it was a way to interface with your APIs or your services. And this wasn't specific to Kubernetes, by the way. This could be an API that is serviced up through a VM, through a function, through a container. through anything, to be honest, or maybe through an external other entity. But the API gateway would be the front door to those APIs, to the way you access those APIs. The API gateway also allowed you to do things like blue greens, canary deployments, dark launches as well, very similar to what a service mesh does. But the thing is, it was just a single entity that sat at the edge of your cluster or at your environment. So what really happened was service mesh is the next iteration of what API gateways do. In fact, a service mesh is just an API gateway that just runs everywhere across every single workload that you have if you choose to, and still honors the same patterns, provides the exact same capabilities as an API gateway. So really, what would have happened is, okay, you might have used an API gateway in your environment for a long time, and now you gravitated towards using a service mesh because your needs have grown and you have service to service communication and interdependent services that can't take advantage of an API gateway but can take advantage of the functionality inside of a service mesh. So today, if you're specifically tied into Kubernetes and you also use virtual machine workloads, there are service meshes, specifically the Istio service mesh, that actually has the facility to provide connectivity across those types of workloads. So it'll provide an API front end for both your VMs as well as your services inside of Kubernetes. Um, if you are just strictly in the virtual machine world, you are better off, leveraging just straight up API gateways due to the nature of and coupling of your services and the way they function, right? So for the majority of users today, especially as they have gravitated towards leveraging Kubernetes, the natural course would be to pick up a service mesh and leverage it on top of your existing systems and platforms.
I, yeah, thanks, Marino. So I hope that it was very insightful and probably all the people out here understood what on a high overview it is. So I think we are also running out of time and it's already about to be 1 hour. So Marino, if you have any final thoughts on this space, and then we can end it.
Yeah, actually, I wanted to just expand upon the API gateway functionality for a second. An
Okay.
API gateway also does things like rate limiting. So here's a classic example. You are trying to run 100 requests against a service, for example, an API. That API, if it hits like 75 requests, it gets overloaded. So one way to control that is to stick an API gateway in front of it and use rate limiting to limit how many requests come through to that service, and effectively ensure that it doesn't get overloaded. So maybe you can only do like 60 requests per minute, for example, and then after that minute, then you can go to another 60. So throughout your entire span of an hour, you get 3,600 requests come through because you've rate limited. Whereas if you try to push those full 100 requests through in that 1 minute, your service falls over and now it might be offline. So there's that consideration as well when it comes to leveraging an API gateway. API gateways, like I mentioned, they're also a front door. They also provide a web application firewall functionality, which effectively is a firewall for inbound. So any traffic coming externally to the inbound will filter if there's policies in place for it. Your API gateway can also terminate TLS for you. So if you have to authenticate to your APIs using a token or a certificate or something, the API gateway can be the facilitator and authenticator for you and tie into other systems as well. So it's very, very well rounded. But that was the first iteration before Service Mesh really, came around and stole the show. But if you're at that point right now, a Service Mesh is probably the right fit for you. So just to kind of close off, thank you so much, Akansha, for hosting this space. I really appreciate it. We're going to do more of these, and we're going to get specific in certain areas. Just to close off, right, I talked about 4 key planes, right, 4 key data planes that we expect to see: the physical layer, the software-defined networking layer, the Kubernetes networking layer, and then the service mesh layer. They exist for different reasons, but they all work and intermingle with each other and they're intertwined because of the way our traffic has to flow. But what becomes very important through all of this is that now with everything offering up an API, you can basically codify your entire network stack, treat it as code, treat it as YAML, automate as much as you want, and even tie it into GitOps. Um, if you have any more questions about anything, feel free to reach out to us. I also want to say, if you're very new to networking and you're trying to understand how networks work and you want to get your hands dirty, look for this workshop called Network Foundations at academy.solo.io. It's a workshop that I put together while working for Solo. I still work for Solo, but it's there, and it gives you a hands-on approach to learning the basics of networking from the ground all the way to how networking works inside of Kubernetes. I want to thank you all for coming out today and listening in about cloud native networking and what networking was and where it is today. Again, if you have any questions, feel free to reach out. I'm looking forward to the next Twitter space, Akansha.
I'm definitely looking forward to it as well. So thank you so much, Marino, for sharing your insights, and I really appreciate your time and expertise. So, thank you, audience. I hope you had some good insights about the networking landscape and had good takeaways from this space. And we would love if you could share a thread or write a blog about your learnings. And we will come up with more such spaces, and we will deep dive more into the networking landscape in the later weeks. So, see you. All right, we can end the space and see you in the next one.
Yeah, and one last thing,
So,
one last thing. Don't forget, everyone, if you're on your journey for the CKA, comment on this space and tell us what your journey is about, what you're looking forward towards. I'm going to pick some random winners and hand out Siam Pathak's CKA handbook, which is a very powerful guide to get you through the CKA exam. Take care, everyone.
take care, everyone. Yeah, so definitely please do what Marino just told you. And Siam Pathak's book is really great, like I know. So, yeah, you surely don't want to miss out on that. Thanks, everyone.